pre-calculus students. Welcome to section 7.2 on two variable linear systems. So you worked with linear systems, just checking my board here. I haven't done this with the board a while, so just checking here. You've worked with linear systems since algebra, maybe even pre-algebra. But we're going to take a problem-solving approach and a using matrices approach because we learned how to use matrices, and it's a great way to solve these systems. So for two variable linear systems, we're going to focus on problem solving. And here are our types of solutions. Graphically speaking, you could have two lines that intersect at one point, as you see in this graph. This solution would be called independent because there's one solution, and it's also called consistent because there is a point that is consistently true in both linear equations and that lie on the lines. Here's an example of a consistent system. X plus y equals 4, x minus y equals 2. Graphically, if you solved this problem, you would see that these two lines intersect at the point 3,1, right? That would be really easy for you to draw both of these lines. However, graphing is a way to solve these systems, except for that takes a lot of time and a lot of accuracy, right? We could definitely use elimination or substitution here. We could use algebra, not that hard, right? But we could also use matrices. And just so you know, when you put this system into a 2x3 matrix and you ask it to solve RREF, you do get the solution that x equals 3 and y equals 1, right? So now that we know how to use matrices, we can do that. You could have a linear system that has no solution. Graphically, that would look like this. That would be two parallel lines. They do not have a point in common. That is called no solution or inconsistent because there's no point that consistently makes both linear equations true. That would be an example of x plus y equals 5 or x plus y equals -2. If you put this matrix into a 2x3 and ask for a solution, what you would get is a top line that you cannot read. X plus y equals 0. And notice that there's many solutions to x plus y equals 0. So you haven't come up with one solution for x and y. So when you try to read the last row, it says that 0x's plus 0y's equals 1. And that's never true. 0x's is 0 plus 0y's is 0. That would say 0 equals 1. That's never true. And that means that's how you know that you have a linear system that has no solution. You can write the equation you can write a linear system that has infinitely many solutions. In other words, I tried to make a blue and a purple line on top of each other here. In other words, they're actually the two lines in the system are the same line, right? And they just look different. So there would be infinitely many solutions if there's a point, every point that lies on one line lies on the other, right? And that would be these two lines here would be an example of that. If you put this matrix into your calculator, again, you wouldn't be able to read the top row. It would say x plus y equals 2, right? There's tons of x and y points that make that true. So you go to the last line and you see that it says 0x plus 0y equals 0. Notice that's always true, and that's how you know that there's infinitely many solutions on a matrix. So let's do some examples. On a matrix, so we're going to put this in the calculator. We could graph this, or we could use algebra also, but I'm going to do a second matrix, and I'm going to edit matrix A. It is a 2x3. I'll be putting in a -1, a 4, and a -14 into the top row, and a 3 and a 1 and a 3 into the second row. And I'm going to second matrix math, RREF. There we go, and pull up matrix A. And we have a solution of 1, 0, 2. 0, 1, negative 3. In other words, x equals 2 and y equals negative 3. This is an example of an independent one solution system. Let's go ahead on B. Let's put this equation into our calculator. Let's see, we have a 2, negative 1, and 5 in the first row, negative 4, 2, and 16 in the second row. And second matrix, let's do RREF. And I'm going to pull up matrix A. And I get 1 and a negative 0.5 and 0 and 0, 0, 1. Notice again, I can't read a solution from the top row. The bottom row shows me that this is no solution. Let's put in matrix C into a 2 by 3. That's 2, negative 1, and 5, negative 4, 2, and negative 10. That's RREF. And we get, in this case, again, a top row that we can't read and a bottom row with all zeros, indicating infinitely many solutions. Awesome. Let's try some problem solving. Two planes start at LAX, that's Los Angeles Airport, and fly in opposite directions. The second plane starts a half hour after the first. Don't you hate these problems, right? Just like the worst of the math, any reason why you don't like a math class, right? Uh-oh, instead of trains, it's planes, right? So the second plane starts a half hour at the first, but its speed is 80 kilometers faster, of course, right? Find the speed of each plane. If after 2 hours, the planes are 3,200 kilometers apart, we're going to use distance equals rate times time. So this really just takes practice, is what it takes. So notice, I think I'll make a list here. I'm going to make X my first plane speed. And I'm going to make Y the second plane speed. But notice, I don't really need that, do I? Do I really need a second variable? Because the second plane, its speed is 80 kilometers faster than the first plane. Oh, okay. All right. I can do a little bit better than that. X plus 80 then equals the second plane speed. All right. No need for a second variable here. That's kind of nice. So again, let me read that. The second plane starts a half hour after the first, but its speed is 80 kilometers faster, right? The second plane is going faster, just checking that out. All right, let's get some more information now about the first plane. Find the speed of each plane if after 2 hours, the planes are 3,200 kilometers apart. Notice the first plane has been in the air for 2 hours, and the second plane then has been in the air a half hour less than that. Okay, so I do have a rate for each of the planes and a time. Okay, well, an expression for that, right? So, and we know that rate times time equals distance. All right, so let's go ahead and solve this then. So the planes are flying in opposite directions, meaning if I add up their distances, it would equal 3,200 kilometers. So the distance of the first plane plus the distance of the second plane equals 3,200 kilometers. But I don't have those distances, but that's okay. I do have rate times time for the first plane. Rate times time plus rate times time. Okay, so the rate of the first plane times its time is 2x plus the rate of the second plane times its time is 1.5x plus 80, and that should equal 3,200. Okay, let's take a look. When we distribute here, we have 1.5x plus 2 x's. That's 3.5x plus, let's see, 1.5 times 80 is 120 equals 3,200. Okay, some quick math in my calculator. I am going to subtract 120 and divide by 3.5 to get my x. 3,200 minus 120 divided by 3.5. 880 kilometers per hour, which means that the second plane, so that's the first plane speed, the second plane speed would be 80 more than that, 960 kilometers per hour. There we go. So no need for a matrix here. Actually, no need for a second variable, right? But it certainly is a linear problem, and it is problem solving, and it's in this section. So I wanted to show that to you. So let's try one more problem. All right, last problem. So Mrs. Hill needs 10 gallons of a 20% acid solution for a lab, but she only has 5% solutions and a solution in a 50% acid solution when she goes into her storage room. She has plenty of it, of the 5% and 50%, but no 20%. So she could combine the 5% solution and the 50% to get her 10 gallons of 20% solution. The question is, how much should she use of each? So let's make X the gallons of 5% solution and Y the gallons of 50% solution. Okay, there we go. Now, we do have two variables in this case, which means we need two equations. And so that means we need two totals. So here's what we need. The first equation is a little easy. When she adds up the gallons of X and the gallons of Y, she needs 10 gallons, okay? So this is the total that she needs of solution, right? The second equation then is, but it has to be 20% acid. So I need an equation for an acid solution. So what I'm going to do is my X needs to be, it has, with how many gallons I have of X, 5% is acid. So if I take the gallons of X and multiply it by 0.05, I get the amount of acid in those gallons. So I will do the same for Y. That would be 0.5 times Y would give me the acid with the Y gallons. And I need that to be a total of 20% acid in the 10 gallons. Right? So I have acid plus acid equals acid in the final product. Let's clean the second equation up a little bit. Right? So 0.2 times 10 is 2. So my actual system now that I will put into the calculator is right here. So let's go ahead and put this into the calculator under a 2 by 3. So we have 0.05, 0.5, and 2. And our second row is 1, 1, and 10. There we go. RREF. There we go. And that says I get a decimal, so I'm going to hit math and fraction. There we go. That Mrs. Hill should use for solution X 20/3 gallons and for solution Y 10/3 gallons. And if we took time to check it, we would see that these two do add up to 10, right? 20/3 plus 10/3 is 30/3, which is 10 gallons. And if we took the time to put it in the acid equation, she would also have the proper amount of acid in her 10-gallon solution. So thanks so much for hanging out with me on section 7.2 and have a good day.